In this video, what I want to do is briefly go over one of the simplest applications of singular value decomposition, which is image compression. So just to start off, this code right here is actually taken from a blog post. Uh, do check the blog post out. It's going to be in the description. I'll leave a link to it. And basically, the blog post goes much more in depth of this application than I will. Right? I just want to show you guys this cool application, but the blog what the blog post does it is that it actually explains how singular value decomposition is more of a transformation applied on inputs, and it's really great. Do check it out. Right now, just to show you guys how this Python program works, right? As an explanation, just know that what this program does is that it takes an image, right? And then it assigns each pixel in that image a value, right? And then what we do is create a matrix out of those values, right? It's really important that we create a matrix out of those values because then we can apply this singular value decomposition on that matrix, all right? We can decompose it into the matrix U, the matrix sigma, and the matrix V transpose. Now, to show you guys the image that we're going to work with today, let me just run this Python file real quick. And you should see the image pretty quickly. Yeah, here. So this is the image we're going to work with today. And so the idea behind singular value decomposition is that what basically when we take away certain information from this image, the quality of the image is reduced, right? But the image itself, like the main components of the image, are still there. All right. So in order to basically reduce the quality of image, what we can do is remove certain singular values. All right. Or basically just consider a small number of singular values to basically reconstruct this image into a low quality image. All right. So to show you how much information is available in this image, what I'm going to do is simply print out the length of the matrix sigma. All right. Oh, also note that this numpy singular value decomposition right here, actually what it does is that it doesn't create a diagonal matrix S. It just creates a one-dimensional array of all the singular values, which in a sense is much more simpler to deal with. So yeah, let me just print out the length of the matrix S, and you'll see once I press this button. Let's see what happens. Yeah, it takes a while to load the image, right? And there's a good reason why, because if you look right here, we have over 2,400 singular values in the image. So the image contains a lot of information, right? Which is why it took a lot of time to load that image, because it was computing so many eigenvectors and all these singular values, right? It took a lot of time. And so we know how much information the image stores. Now, what I want to do is compare the length of those. Sorry, not the length, but let's see what the values of those specific singular values are. So what I'm going to do is just print out the first 10 values of the singular value matrix. Sorry, the array. So I'm just going to print out the first 10 values. And then I'll also print out the last 10 values. How about that? Let's print out the last 10 values. and see what we get. All right, again, it's going to take a lot of time because it's doing a lot of computations. All right, we have our image. Okay. Oh, here's an error. But if you look at here, we got the first 10 values of the array. And you can see they're pretty big, all right? This one's almost 600K. This 55,000, 31,000, 11,000, right? These are pretty big numbers. Now, let's print the last 10 singular values of the array. See what we get. All right, let's get rid of this. All right, so this is our first 10 values of the first 10 singular values of the array. And this is our last 10 values of our array. So you'll probably notice that the singular values are decreasing across the array, right? As you go across the array, the values decrease, and this makes sense because in the last video when I talked about singular value decomposition, I noted that in the diagonal, as you go across the diagonal, the values of singular value, uh, the singular values are decreasing basically, right? And yeah, and another thing to note is that these small values right here basically serve little, they have little contribution to the overall quality of the image, all right? Um, they're so small that they just can't contribute, right? So just taking away these values, these taking away this information from the image really doesn't do anything, all right? We still maintain that quality, you know, but what the result is that we get a basically compressed image that stores less information, and it still has kind of the same quality. Now, I just want to show you guys how it would look like, basically. So here I've written this code that, and you know what? It's annoying that we have to wait for this thing to, we have to wait for this code to load the image. So I'm just going to skip right into this part of the code. And what this code does is that it asks the user for a value, right? And then what we'll do, basically the value is for the amount of singular values that we want the image to store, all right? Once we've shown that, we get something like this. So I'm just gonna wait here. Um, yeah, okay, now it's asking us for an integer value. So I know that there are over 2,400 singular values here. But what happens if we consider only 10 of the singular values? What would happen to the quality of the image? Let's see. Oh, interesting. So we can still see this cactus right here, but it's just low quality, right? And so it's pretty cool. We compressed the image down from 2,400 singular values all the way to 10 singular values. And although the quality has been affected, we can still see the image, which is crazy. Now, of course, if we wanted to use this image for, if we wanted to use this image for, let's say, a project or something, we want a nice image. I don't want this ugly image, right? So let's play around with this, and let's try adding 100 singular values, okay? But let's not add like 2,000 singular values because that would take a lot of, yeah, that would take a lot of computations. So let's add 100 singular values and see what we get. Yeah, see, that's a good quality image, right? And all right, so there we go. All we need to do is just type a number here, and we got basically a nice image. right? And we don't need a lot of information, right, for the image to hold. And let's see what a 2400, let's see how much information 2400 singular values can hold. So let's try adding number 2400. Okay, yeah, honestly, if you ask me, I really couldn't tell a difference between 2400 and 100. So yeah, I mean, that's pretty cool. I guess you can see these little spikes more clearly when you have 2400 singular values. But other than that, I mean, yeah, it's pretty cool that all you needed to basically make up the image was just 100 singular values. Now, we played around with this code right here, we tested it. We saw that we don't need all the information in an image. We can actually get rid of some of that image. I mean, get rid of some of that information to reconstruct the image into a more basically compressed package. Now, what I want to do is create a plot that shows the value of singular values as we go across the array, this array S. So let's get rid of this. And yeah, okay. Now let's run this code right here, all right? What this code does is that it plots a graph of singular values with respect to the index of the singular values in the array S. So let's see what we get if we create this plot. All right, this is the plot we get. This is not the most clear plot. I can see here at 0, at singular value index 0, there's a very steep line here. And then very suddenly we go down to 0 and then we get this plateau. This is not very clear. Let's put this plot into a log scale. So I'm gonna put this into a log scale. And let's see what we get. All right, this is kind of clear, I guess. We see that as we go across the array of the matrix sigma, or sorry, the array sigma, I guess, the values are definitely decreasing, but initially they're decreasing at a rapid rate. However, then we see a slow change in the decrease, and then finally it stops, right? So yeah, that's pretty cool. So we started off with like almost 600K. You go end up at like 100, keep going down, and then you saw that the last 10 singular values were basically decimals, less than 1, right? So that's pretty cool. And also note that all the singular values are positive, none of them are negative. If you want to know why, go check out my previous video on singular value decomposition. But yeah, this is pretty cool. This plot does tell us how much information we truly need. So again, as a rule of thumb, if I wanted to reconstruct this matrix, I said that 100 singular values were enough to reconstruct the image instead of using all the 2400 values. I don't know, but I mean, I feel like this image can still hold more information, would benefit from holding more information. So around this 10 to the power of 1 here, I think. Like 1500 is probably a good rule of thumb. I guess having 1500 singular values, still a lot of computation, but it will provide you with a good quality image. But yeah, so that was the purpose of this video. Again, I've just started looking into this application, so probably there's something I'm missing out on. Do let me know if there's something I'm missing in my thing right here. But yeah, also check out the blog post that I'm gonna leave in the description. It's really gonna help. So yeah, thank you very much for watching this video.